Hi, I'm Brandon Graysley. I'm a high school math teacher. We're going to look at the sine function today. This is what we use when the sine ratio fails us. Here's a right angled triangle, a right triangle. There's an angle theta. And we have two short sides here and one long side. This long side we often call the hypotenuse, and this is the opposite side. Opposite because it is across from the angle we're interested in. And this is the adjacent side. We'll usually use these three short forms. And we know that the sine ratio for theta, sine of theta, is equal to the length of the opposite side divided by the length of the hypotenuse. So if I were to put in some specific values here, like let's say that's 3 and that's 4 and that's 5, it's one of our nice triangles, the sine of theta, that ratio will be 3/5 or 0.6, which is wonderful. Except sometimes we have triangles that don't look like this, that aren't nice right angle triangles. Maybe something like this, which has an obtuse angle in it, a big angle that is more than 90 degrees. So you can see that there is no way to have a right triangle with a large angle like this in it. There wouldn't be enough room for that many degrees in a triangle, which can only have 180 degrees. And so we need something different. We've got to find a different way to define our sine ratio so that we can use it on big angles. And so fortunately, we do have a way to do that. And we're going to use what's called the unit circle. This is a circle, which I have drawn using the canning seal of mathematics. And this distance here is 1. That's the point 1, 0. That is the distance from the origin is 1, and that's why it's called the unit circle. Unit meaning 1. This circle has a radius of 1, which means this length here is always 1. Right there. Any line I draw from the center of the circle, the origin, out to the edge, to the circumference, that has a length of 1. So I've drawn this one in a special place. This spot right here, we're going to call this x, y. The special place I've drawn this is in the first quadrant, in this section right here. And the angle in here, I'm going to call, you guessed it, theta. So here's what's interesting about this. If I want to know the measurement of this angle theta, what I can do is measure the length of two lines. This line here, ooh, I should have used the ruler of mathematics, that line there, and this other line right here. Well, how long are those lines? Well, let's see. This distance from the x-axis up to this point is the distance, is the value y. That's the length of this. That's what the y-coordinate means. It's that sort of height on the axis there. That's length y. All right, that's pretty nice. And similarly, this distance out here is x. That's pretty cool. So, well, this is just a little right angle triangle. That's fine. We can use our sine ratio the way we have been. The sine of theta is equal to the opposite side. In this case, it's the length y, the value of y, divided by the length of the hypotenuse, which we carefully crafted as being the value 1. So sine of theta is equal to y. That's pretty sweet. For example, let's put in our actual values from before. Let's say I have the same triangle as before. That will make up my x and y values. X would be 0.8 and y would be 0.6. You'll see if you multiply those numbers all by 5, you'll get the same numbers as we had before. So if that's a point, if that's this point here on the circle, the sine of our angle, theta, is equal to the y value. That's it, 0.6. And so if you wanted to know what theta itself is, you would take sine inverse of that value here, and I grab my calculator of mathematics, 0.6, and then I choose my sine inverse function, and it tells me that that is about 36.9 degrees. Okay, that works pretty well so far. But as I said, we're going to run into trouble when this angle gets really big, and we have to pass beyond the 90-degree mark here. So let's do that right now. Let's choose an angle that's over on this other side. That is a big angle that starts here still, but goes past the 90-degree mark. Let's pick one that's pretty easy to find. Let's go over here and like this. And that point is the point negative 0.6 and positive 0.8. You might see some familiar values there. I will grab the ruler of mathematics here. And so I've drawn now a line, and I want this angle here. Let's use a different letter instead of theta. Let's use beta. That's kind of B-like with a little line on the little tail on it. To find that length here, I want to use the same sort of process as before. Let me just draw that vertical line again. And I've got another horizontal line here. Now, instead of the actual length, we're going to still use the y coordinate. In this case, it's still 0.8, but it's just sometimes you're going to get some of these negative values, and we want to be careful to include them where necessary. So the sine of beta is going to be equal to the y value, which is 0.8. Okay, and then if I take sine inverse of 0.8, I'm just going to put some exclamation points here right now because I want you to be really careful about this and watch what happens. If I just punch in 0.8, I'll put this right here, and sine inverse, what do I get? 53.1 degrees. Wait a second. That doesn't make a lot of sense, does it? Because this beta value should be more than 90 degrees. And here we have a problem. The problem is sine can't tell whether this 0.8 is here or over here. There's no way for the sine function to know which quadrant you're in. And so you have to use your brain a little bit extra here. You have to know a little bit about your angle. So if I know that this is an angle that is on this side of the y-axis, it's over here in the second quadrant, then it's not 53.1 degrees. It is 180 degrees minus that value, minus 53.1 degrees. So on my calculator, the way I like to do this, I like to hit the plus minus button to make that negative, and then add 180. And that gives me 126.9 degrees. That is beta. And this is always true. Any angle that you have here, if I have an angle like this, there's a corresponding angle on the opposite side that has the same y value, and therefore it has the same value for the sine function, but the two angles are different. I have this little angle here, and I have this big angle, which is 180 minus the little angle, because I have the same little angle on this other side. So that's always true with sine, that you got to watch which quadrant you're in. And unfortunately, this is not the only place we have this problem. We also have the same problem on the bottom of the circle in quadrants 3 and 4. So let's try those out. Here I have another unit circle of mathematics. And suppose I have a point that's down in here somewhere. Let's say, let's just go right over to the same kind of area. We'll go negative 0.8 and negative 0.6, which would be somewhere around there. Negative 0.8, negative 0.6. These numbers just work out awfully nicely. We could have used anything. So let's draw in our line again, and let's just remember what angle it is we're talking about. We're now talking about this very large angle here, like this, and let's call it delta. I like delta. It's sort of like a D shape. And so this angle we know should be more than 180 degrees. See that? There's 180, and we're going to get a little bit beyond that. Well, let's see the coordinates here. We got still have our little triangle. You might think of this as negative 0.8 here and negative 0.6 down there. So the sine of delta is equal to this y coordinate right here, negative 0.6. What happens when I take the sine inverse of negative 0.6? What do I get? So 0.6, make it negative. second function, sine inverse. Okay, that's interesting. I got a negative angle, negative 36 point, let's say 36.9 degrees. What could that mean? Well, that is the same as if I had this same angle on the other side over here, and I sort of go backwards from the beginning, from the positive x-axis over here. That would be sort of negative 36.9 degrees. And so, hey, just like before, we're going to take this value and we're going to see where we are compared to 180. That's actually a negative value, right? So if I take 180 degrees and I subtract this negative value, I'm going to get delta. Check it out. So 180 minus, and then I'll put it in here, 36.9 with a negative sign equals, I'll get a bigger number, 216.9. All right, that's pretty nice. So what I have then is if I get a negative value here, then I know I'm either in quadrant 3 or 4. Sorry, 3 or 4, this one over here. And since I happen to know that I'm in quadrant 3, both my values are negative here, that means that I take 180 and I subtract that negative number, or if you like, add the positive version of it, and I got 216.9 degrees. That's that angle all the way around there, past 180, and into this section down here. All right, well, let's do one more. What happens if we are in the 4th quadrant? What happens if my value is something like this one here, which in this case is positive 0.8 and negative 0.6. Let's draw our line here again, and we'll draw our vertical line up to the x-axis. This angle now is starting at the positive x-axis, comes all the way around here like this. That's the angle. This is a big angle. This is almost 360 degrees. We're getting pretty close when we get into this quadrant. And so let's call that angle, what have we not used? We haven't used gamma yet. It's sort of like a little loop, like a ribbon. So that angle gamma, what could it be? Well, once again, we know that the sine of gamma, ooh, that's a pretty big loop. The sine of gamma is negative 0.6. Hey, we just calculated that. The sine inverse of negative 0.6, we know, is negative 36.9 degrees. We just did that up here, see? Well, okay, that's pretty nice actually, because what this means is if I take 360 degrees and I add that negative number, or maybe I'll just say subtract 36.9 degrees right here, I get 323.1 degrees, which is the value of gamma. So you've got to know a little bit about your angle to know where you're going to be placing it. If it's from here to here in the 1st quadrant, it's between 0 and 90 degrees. 90 would be right on the line. Then you have 90 to 180, 180 to 270, and 270 up to 360. And here's the really neat part. If you keep going, if you have an angle that is even bigger, that goes off into the next, the 1st quadrant again, say an angle like 400 degrees, well, the sine of 400 degrees, let's try it, 0.64, that is the same as the sine of 360 less than that, which will be 40 degrees. 40 degrees, hit the sine function again, is also 0.64. And so any angle that you have, you can either add or subtract 360 to it, and you'll get the same value for sine every time, because sine is a periodic function. So over and over and over again, you can circle around here as many times as you want, and you're going to end up with the same values out of the sine function. And so next we're going to look at what does the sine function look like if you graph graph sort of horizontally. What are all the sine values as x goes up? And just as a quick sneak preview, it looks kind of like this, and we end up calling it a wave. I hope that helps you to understand how the unit circle works and why we need the unit circle because the sine ratio just isn't enough for us. Right angle triangles are too small. Thanks.